All right, let's get started today. So we will share our screen. Share screen, the entire screen. Yep, looks good. And let's record just in case.
Recording in progress.
Hello, everyone, and welcome back. We are continuing on with our ILC learning course. So this is the MCT4C course. This is the Unit 1 review. And I believe, according to my notes here, this is our 10th lesson together. So it's gonna be so looking forward to that. Very exciting. Uh, Unit 1 by far is one of the longer lessons, longer sections. Unit 2 is a bit shorter, and Unit 3 by far is the shortest one to go through. And so for today's lesson here, we're going to be doing a survey or a review of topics from Unit 1. Mainly, we're having a look at our exponent laws, solving exponential equations, our introduction to logarithms. We're going to solve logarithms, and in general, have a look at polynomial functions. And it's worth noting that after this unit, we're going to continue on with studying polynomial functions, and we're going to be looking at long division for a couple of days. So we have that to look forward to. And so And again, this would be an excellent time now if you've been following along. You can download the notes on my Google Classroom. It would be an excellent time for you to go ahead and pause the video and try these questions for yourself. You can, just because this would also make an excellent exam review as well. So I do recommend you try that out. Okay, so we're going to simplify the following and we're going to express our solutions using positive exponents. So we're going to go all the way back to Unit 1 and let's get started. So here we have the quantity 5 multiplied by a times b to the power of 6 divided by a to the power of 2. Now, first thing I'd like to do is to expand that 6 onto the ab. So this becomes 5 multiplied by a to the power of 6 multiplied by b to the power of 6 divided by a to the power of 2. So this was the power of the power rule. Next thing we want to do is to simplify this down. So note that uh, there are no other constants except for the 5, but we have a to the power of 6 divided by a to the power of 2, which means we're going to keep the base and subtract the exponents. So this will become 5a. Now, a to the power of 6 divided by a to the power of 2 is the same thing as a to the power of 6 minus 2, which will be 4. And then we tack on a b to the power of 6 at the end. And that's it for that question. Letter B, we have in brackets 3 divided by m times n to the power of negative 2. So first thing we want to do is use, and I would recommend this is just to apply the negative exponent. And so when we apply a negative exponent, that means to take the reciprocal of the inside. So recall that if you have, say, a over b to the power of negative 1, that's the same thing as b over a, say, to the power of 1. Or if you prefer, we can say negative m and positive m. Okay, so 3 over m times n becomes the same thing as m times n divided by 3 to the power of 2. We now want to apply that exponent 2 onto all terms on the inside. So mn becomes m to the power of 2 multiplied by n to the power of 2 divided by, now we have here 3 to the power of 2. And recall that if you have 3 to the power of 2, that's the same thing as 3 times 3, which is 9. So our final solution will be n to the power of 2 multiplied by n to the power of 2 divided by 3 to the power of 2, which is 9. Okay, let's carry on. Letter C here, in brackets, we have 5a to the power of 2 divided by 3b to the power of 4, all to the power of negative 3. Okay, fair enough. So first thing we're going to do is apply the negative exponent. So that means we're going to take the reciprocal of this, and this will give us 3b to the power of 4 divided by 5a to the power of 2, and all of this is then to the power of 3. Now we apply the negative 3 exponent onto all terms. So just remember that when you apply it to a constant, remember that the constants have a power of 1. So if you have 3, 1 to the power of 3, it becomes 3 to the power of 1 times 3. So this will be 3 to the power of 3 multiplied by b to the power of 4 times 3 is 12, divided by 5 to the power of 3 multiplied by a to the power of 2 to the power of 3 is the same thing as 2 times a to the power of 2 times 3, which will be 6. Okay, 3 to the power of 3 is going to be 27. And again, you can refer to those power of a power charts just because it's quite helpful to commit those to memory. So it's 27 times b to the power of 12 divided by 5 to the power of 3 is 125 times a to the power of 6. Let's go ahead and clean up that one a bit here. Okay. For this page here, because we still have some more to go through, we have m to the power of 1/3 multiplied by m to the power of 2/3. And so you want to keep the base and add the exponents. So that'll be the same thing as m to the power of 1/3 plus 2/3. And remember, when you're adding or subtracting fractions, you want to make sure the bases are the same. In this case, they're both 3. So this will be the same thing as m to the power of 1 plus 2 divided by 3, which is the same thing as m to the power of 3 over 3, which is just m to the power of 1, which is simply m. Surprisingly, this ended up having more steps than all of the previous questions, but these things happen. Now, again, when it comes to fractions, recall that when you add or subtract fractions, the denominator represents the size of the slice, right? So if you have half a pizza plus a quarter of pizza, you actually have 3/4 of a pizza. So I know that some of our people are in Sioux Lookout. So, if you think about like a Wellington pizza as an example. Okay, let's continue on. So E, we now have 4 times c to the power of 7 over 9, all to the power of -2. Okay, fair enough. First thing I want to do is just apply the negative exponent. And so this will become, and recall that if you have, say, the number 4, that's the same thing as 4 over 1. And conversely, in this case, if you happen to have 4c to the power of 7 over 9, you can put this over 1. The reason why we want to do that is because then we can then apply the reciprocal. And so we'll end up with 1 over top of 4c to the power of 7/9. All this is to the power of 2. Next thing we want to do is apply the exponent of 2. So 1 to the power of 2 is simply 1 over top of 4 to the power of 2 multiplied by c to the power of. Now, we are multiplying, we have c to the power of 7 over 9 to the power of 2. So we want to multiply those two fractions. So note that if you have 7 over 9 times 2, that's the same thing as times 2 over 1, which means it's going to be 14 over 9, which will be our solution. That's good enough for us, but do recall that this will be the same thing as 1 over 4 to the power of 2 is 16. And if you have c to the power of 14/9, that's the same thing as the 9th root of c to the power of 14. Or if you prefer, you can write this as the 9th root of c, all to the power of 14, depending on what your preference is. Either is okay. All right, so do recall here that as a note, that if you have c to the power of 14 over 9, that's the same thing as the 9th root of c to the power of 14, which is also the same thing as the 9th root of c to the power of 14. So either you can apply the index first, where, what number times itself 9 times produces c, and then all of that is to the power of 14, or you can take c to the power of 14 and then do 1 over 9. Do remember from our studies that typically, if we're going to have to be using this middle form, the 9th root of c tends to be more helpful. Okay. At any rate, let's continue on. So for f, we have 5u to the power of 3x plus 1. So recall that the entire exponent is 3x plus 1, multiplied by 20u to the power of 4x minus 1. So that means we can just add these exponents together. Okay, and so, oh, I should also mention, and perhaps we'll just show this as a little note here, we have two constants out in front, so we can actually just multiply those quantities together. So 5u to the power of something times 20u to the power of something is the same thing as 100 multiplied by u to the power of 3x plus 1, all multiplied by u to the power of 4x minus 1. Okay, so the constants can just be multiplied together. And then we just add the exponents. So this will be 100 times u to the power of, and that exponent will be 3x plus 1 plus sign 4x minus 1. We don't need any brackets in the exponent because we're not subtracting anything. And when I say subtracting, I mean like we're not subtracting an entire quantity. Okay. And so we get as a solution that this will be the same thing as 100u to the power of 7x minus 1. And just as a note for convention purposes, just leave linear exponents as is. Can't really simplify that down anymore. Like if you try to take out a negative, or maybe if both terms were negative, like the 7x minus 1, once it's there in any configuration, just kind of just leave it be. You don't try to do anything more with it because we really can't. Okay. Letter G, we have y to the power of 1 over 5, all to the power of negative 4. So here, I would actually just say we can either, no, we should just apply the negative first. We've been pretty consistent about that this whole time. So we'll go ahead and do that. So this will become 1 over y to the power of 1/5, all to the power of 4/5. Okay, because you want to take the reciprocal. Now we need to multiply the exponents. So 1 to the power of anything except infinity is going to give us 1. So that's okay with us. And in the denominator, y to the power of 1/5 all to the power of 4/5 is the same thing as y to the power of 1 over 5 multiplied by 4 over 5, which simplifies down to 1 over y to the power of, okay, so 1 times 4 is just 4, 5 times 5 is 25. So when you multiply fractions together, you want to multiply the numerator, multiply the denominator. Okay. Trickiest one for us to go through is letter H. We have here u to the power of 5 multiplied by v over top of u to the power of 3/7 times v to the power of negative 1/2. And for this kind of thing, it's kind of, if you're not sure about the fraction work, just do it off to the side. So here we're going to have an aside, and we're going to show our work over here. Okay. And so here, one of our calculations we're going to run into is we have u to the power of 1/5 divided by u to the power of 3/7. Okay. And in fact, we can show that step over here. So we have u to the power of 5 minus 3/7 times, and then we're going to end up with v divided by v to the power of negative 1/2, which will be this v to the power of 1 minus sign no matter what, negative 1/2. So let's go ahead and do these calculations. So if we have 5 minus 3 over 7, keep in mind we need a common denominator. Common denominator here is going to be 7. And so if we multiply top and bottom both by 7, 7 times 1 is 7, 7 times 5 will be 35. And so we have 35 over 7 minus 3 over 7, which is going to be 32 over 7. And again, don't do mixed numbers. That's not what we want to be doing here. And if we have 1 minus sign, negative 1/2, this is the same thing as 1 plus a half. And you might be thinking intuitively, if you have a full slice of pizza plus half a pizza, that means you have 3 halves, right? Yes, or you have 1.5. But again, we want to write this as an improper fraction or combine them into a single term. So 1 is the same thing as 2/2 plus 1/2, which becomes 3/2. And so going back to our main calculation here, and again, it's okay to show this kind of work off to the side if you think it's going to be too clunky to show. I do it all the time when I want to make sure I preserve understanding. Okay, so we're going to end up with u. Now 5 minus 3/7 ended up being 32/7 multiplied by 1 minus a negative a half is the same thing as v to the power of 3/2. Note that those exponents are both positive, so we're quite content to leave them as is. Okay, so that's the end of the exponent law review. Let's continue on. So example 2 was solving exponential equations. So I included as a little reference for us our powers chart that tends to have all the ones we could need. And so let's go ahead and see what this question wants. So we're going to solve each of the following exponential equations by expressing both sides with a common base. Okay, so that means we want both sides to say like 7 to the power of something. And then at that point, the goal will be to equate exponents. So what we'll do is afterwards, we will equate the exponents. Okay, so for letter A, we have 3 to the power of 7x minus 3 is equal to 81 to the power of x. So you see that 81 there is the same thing as 3 to the power of 4. And so what this will become is 3 to the power of 7x minus 3 is equal to 3 to the power of 4 all to the power of x, which becomes 3 to the power of 7x minus 3 is equal to 3 to the power of 4 to the power of x is the same thing as 4x. We can now equate the exponents. So we have 7x minus 3 is equal to 4x. Let's subtract 7x from both sides. I know we typically like having our x's on the left side, but in this case, it's not going to be too much extra mental effort. So 4 minus 7 of the x variety will be negative 3x. And dividing both sides by negative 3 yields that x is equal to positive 1. There it is. Okay, letter B, we have 25 to the power of 4x plus 3 is equal to 125 to the power of 3x. Fun fact, if a number ends in 5, it's always divisible by 5. And in this case, we can see that 5 to the power of 2 is 25, and 5 to the power of 3 will be 125. So we can rewrite 25 as 5 to the power of 2, all to the power of 4x plus 3. 125 is the same thing as 5 to the power of 3, all to the power of 3x. Multiply the exponents together. So this will be 5 to the power of 2 multiplied by 4x plus 3. Again, a little bit of a problem note here. Just note that it's 2 times the entire quantity 4x plus 3. So you need to make sure you put a bracket there. The mistake I see here is students would write this as 2 times 4x, which is 8x, and then tack on the plus 3, but it should be plus 6, because remember, it's 2 times the whole quantity. 5 to the power of 3 to the power of 3x is the same thing as 5 to the power of 3 times 3 of the x variety is 9x. And at this point, we can equate the exponents. So we're going to have 2 multiplied by 4x plus 3 will be equal to 9x. So 2 times 4 of the x variety will be 8x. 2 times 3 is 6, as stated earlier, is equal to 9x. Moving the x's to the right side seems to make sense. So 9x minus 8x will be 6. So in fact, x is equal to 6, or if you prefer, you can say 1x is equal to 6. And as always, if you so wish, you can go ahead and check your answers on your calculator. Today I have the Desmos scientific calculator and the Desmos graphing calculator in case we need them. Okay, letter C, we have here 7 over 2 to the power of 3x is equal to 4 over 29. And so the way to do this is to note that we can see that we've got a 7 and a 49, and we've got a 2 and a 4. So that's already a little bit of a hint that we should be finding a common base of this some kind, namely that 2 to the power of 2 is equal to 4, and 7 to the power of 2 is equal to 49. And so the only thing, though, is that we can see it's 7 over 2, but we need 49 over 4. So we could take the negative reciprocal as a first step. Okay, I got plenty of space. So this will be 7 over 2 to the power of 3x is equal to, now we're going to take the reciprocal. So this will be 49 over 4 to the power of negative 1. And if you're unsure about what you're doing, you can just reapply the exponent to make sure that things appear to be going according to plan. Okay, so now let's continue on. 49 over 4. Well, 49 is the same thing as 7 to the power of 2. 4 is the same thing as 2 to the power of 2. And so what we end up with, 7 divided by 2 to the power of 3x is equal to 7 to the power of 2 divided by 2 to the power of 2, all to the power of negative 1. And so we have 7 over 2 to the power of 3x is equal to, now note this has a 2 applied to both, and so this becomes 7 over 2 to the power of negative 2. Because remember, this was part of the expanded exponent laws, where if you have a 2 applied, an exponent 2 applied to both the numerator and the denominator, just pull that out. At this point, we note that the bases are the same, so we can equate the exponents. And so we've got the case 3x is equal to negative 2, dividing both sides by 3. We end up with x being equal to negative 2/3. Okay. Lastly, but not leastly, for the equating common bases, we have the square root of 8 is equal to x plus 2 is equal to the cubed root, or the third root of 32 to the power of x minus 3. So sure, let's go ahead and do this. Now, it's worth noting that the square root of 8 is the same thing as 8 to the power of 1/2. I'll mix up the colors here. 8 to the power of 1/2, all to the power of x plus 2 will be equal to the third root, or the cubed root of 32. So this will be 32 to the power of 1/3, all to the power of x minus 3. Now, consulting the chart, we can see that 2 to the power of 3 is 8, and 2 to the power of 5 is 32. And so we will have here, so keep in mind, a little note here. If you have 2 to the power of 3 to the power of 1/2, this is the same thing as 2 to the power of 3/2. Okay. And so 8 to the power of 1/2 is the same thing as 2 to the power of 3/2, all to the power of x plus 2. And 32, similarly, will be the same thing as 2 to the power of 5/3, all to the power of x minus 3. We can now expand the exponents, or multiply the exponents. So 2 to the power of 3/2 to the power of x plus 2 is the same thing as 2 to the power of 3 over 2 multiplied by x plus 2 is equal to 2 to the power of 5 over 3 multiplied by x minus 3. At this point, we can go ahead and equate the exponents and go ahead and simplify this from there. So we're going to have 3 over 2 multiplied by x plus 2 is equal to 5 over 3 to the power of x minus 3. So what we need to do is to go ahead and multiply both sides by a number such that it'll eliminate the denominators. And so we need a common factor for 2 and 3. That number is going to be 6. So we multiply both sides by 6. So 2 goes into 6 3 times. 3 goes into 2 twice. And so we end up with 9 times x plus 2 will be equal to 5 times 2, 10, multiplied by x minus 3. So now we can go ahead and expand this out. So 9 times x is going to be 9x plus 18. 10 times x is going to be 10x minus 30. We're going to collect the number terms on the left side. So to get rid of this negative 30, we plus 30 to both sides. So this becomes 48. We're going to minus 9x from both sides and x. And so here we have our solution. As it turns out, if you have the square root of 8 to the power of x plus 2 is equal to the cubed root of 32 to the power of x minus 3, the value that makes both of these equations true is x has to be 48. So some huge number. Okay, let us continue on. So remember, as an introduction to logarithms here, what you should be able to do is easily convert from the exponential to the logarithmic form or the reverse. So the idea behind this, and color coding it will take a long time, so I'll just write an example for now. If you have a to the power of b is equal to, say, some capital C, the logarithmic equivalent will be log base A of C is equal to B. So here, if we have the exponential form, 5 to the power of negative 4 is equal to 1 over 625. This is the same thing as log base 5 of 1 over 625 will be equal to that negative 4 value. And if you have something like log base 3 of 243 is equal to 5, remember the way is you start with the base, move it over to the other side, and then say it's equal to that number. So this is the same thing as 3 to the power of 5 equals 243. When in doubt, you can always check your answers to make sure that these are correct, to see that this is the case. Okay. Oh, here I have it backwards. I guess I should have put this one over there, but that's okay. I'll fix that one later. So if we have 4 is equal to log base 9 of 6,561, this is the same thing as 9 to the power of 4 equals this number. So this will become 9 to the power of 4 is equal to 6,561. So no, I just made a mistake on these ones. I just put them in the wrong spot. Okay, and if you have log of 1,000, recall that the base of the log is just 10. So this is the same thing as 10 to the power of 3 is equal to 1,000. Oh, this one was done correctly. I just didn't do that one above. Okay, so the key to understanding logarithms, and pretty much no matter how difficult they get or work with, so if you end up taking the additional math courses, pretty much if you can convert between the two forms, like you're 85% of the way there towards solving these things. Because people tend to forget that that's a legitimate step that you can do. Okay, we're going to sketch y is equal to 1 over 4 to the power of x, its inverse, and the line of reflection. So note that we are sketching, which means the graph doesn't need to be perfect. Okay, so first thing we want to do is get our table of values. So we're going to choose some x and y values. So normal x values that you can pick are, say, -2, -1, 0, 1, and 2, just standard x values. And you want to insert each of these values into your equation for y is equal to 1 over 4 to the power of x. And so if you type in 1 divided by 4 to the power of -2, you will get 16 as an answer. If you type in -1, you'll get 4. If you type in 0, you get 1. If you type in 1, you get a quarter, but we'll write the 0.25 so it's easier to graph. And if you put a 2 in there, you get a 0.0625. Okay, which means when we graph the inverse, f, and remember that the notation for this is f -1 of x, you just switch these values. So -2 comma 16 becomes the 0.16 comma -2. -1 comma 4 becomes the 0.4 comma -1. 0 comma 1 becomes 1 comma 0. 1 comma 0.25 becomes 0.25 comma 1. And 2 comma 0.0625 becomes 0.0625 comma 2. So we're going to sketch. I don't have ruler technology, so all of you will have to trust me that this graph is going to appear perfectly straight. Because some of you might not have graph paper either, and you just want to make sure it's like a reasonable graph. Okay, so we don't have space for all of these, so but again, we'll just try our best. So we'll call this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we'll just label these outside values and have each tick be 1, roughly spaced out. And we'll go ahead and type these in. So the first one is -2 comma 16. Well, that's way up there. We can't fit that one, but we can fit -1 comma 4. So we'll go ahead and sketch that one. Next one is 0 comma 1, which is there. Next point is 1 comma 0.25, which is there. And the next one here is 0.02 comma 0.0625. So there it is here. So here is this particular curve. And it has asymptotic behavior, meaning that as x approaches the positive infinity, it just tends towards 0. It doesn't quite get there. So this, we'll label this the black function here, y is equal to 1/4 to the power of x. This the red function, we just swap the values. So 16 comma -2 is not going to fit, but 4 comma -1, we can fit that one in. 1 comma 0, we can fit this in. 0.25 comma 1, it's about here or so. And 0.0625 comma 2 is about here. And so we have this graph look like this one here. And so this is our inverse function. And the only thing now is we need the line of reflection. So recall that the line of reflection is merely y is equal to x. So this is a dotted line that goes through the origin. Okay. If you have graph paper, ideally you would do this on graph paper so it looks nicer. But again, we try our best to make it look as nice as possible. I have a unit come in at the end of unit 2 and the start of unit 3. We do a lot of graphs, so I actually do provide graphs so that it's a bit neater for us. Okay, let's continue on. Example 4 was solving logarithms, and when I say solve, I mean solve/evaluate logarithms. Example 1 has us evaluate. Evaluate means that we're not trying to solve for an x value, we're just trying to simplify it down. evaluate also could just mean something as simple as, you know, 2 to the power of 5 is 32. That means evaluate, meaning determine the calculator answer. Okay, so log base 2 of to the power of 32. So remember, the key technique we want to use to solve this is that we would like to have a common base of some kind. Checking to see how much time we have. Okay. And so log base 2 of 32 is the same thing as log base 2 of 2 to the power of 5. And the rule that we can use here is if you have log base b of b to the power of n, that's just equal to n. So log base 2 of 2 to the power of 5 is just 5. Letter B, we have log base 6 of 216 to the power of 3. So this is the same thing as log base 6 of 6 to the power of 3, all to the power of 3, which means it'll be log base 6 of 6. Now, 3 to the power of 3 will be 9. And using this rule from earlier, we end up with a 9. So again, quite a helpful rule for us is just this one we highlighted earlier. If you want to see more about the properties, have a look at lesson 4 is where we summarized a chart of them. So that way you can have a look at them. Letter C, we have log base 3 of 1 over 27. So again, we see 1 over 27 and a base of 3. We want to have a negative exponent. So 1 over 27 is the same thing as 27 to the power of negative 1. So remember, this is 27 is 3 to the power of 3. So this will be log base 3 of 3 to the power of negative 3, which is going to be equal to negative 3. And this tricky one is you said, hey, if we have the same base as the argument, but there's variables, does that change? No, you can still apply the rule, right? Because keep in mind, in the rule we used up here, suppose if we had log base b of b to the power of n is equal to n, what if n was 5? Then that's perfectly reasonable for us to evaluate, assuming we have no domain restrictions. And so log base x of 1 over x, and again, we see 1 over x, we want to make it a positive exponent. So this becomes log base x of x to the power of negative 1, which is just merely negative 1. Okay. Let's clean that up a bit. Okay, let's continue on. We're solving some logarithms here. So we have log base 3 of x is equal to 4. So let's use the exponential equivalent and rewrite this as 3 to the power of 4 equals that. So 3 to the power of 4 is equal to x. 3 to the power of 4 we know is 81. Log base 5 of x is equal to negative 3. We know that this will be 5 to the power of negative 3 is equal to our x value. Taking the reciprocal, we end up with 1 over 5 to the power of 3. 1 over 5 to the power of 3 is equal to x. 5 to the power of 3 is 125. So consequently, x will be equal to 1 over 125. Okay. Letter C, we have log base x of 1 over 216 is equal to negative 3. Immediately, you should be suspicious of this and see that it's the 216. So your first instinct is that's probably 6 to the power of 3, right? And it is. It's actually a good idea to start recognizing that right away. And if you want to, you can write this as log base x of 6 to the power of negative 3 is equal to negative 3. Okay, so some of these instincts should be starting to kick in when you see 1 over 216, you should recognize 216 is just 6 to the power of 3, and we probably need a negative exponent. And if you don't, then you'll find that you do. Okay, let's write this in the equivalent exponential form. And so we end up with x to the power of 3 is equal to, x to the power of -3 is equal to 6 to the power of -3. Since the exponents are the same, we can equate the bases, and consequently, we end up with the case that x is equal to 6. Okay. Lastly, but not leastly, we have some sort of we have x is equal to log base 3 of the cubed root of 81. And at this point, questions you should be thinking are, should I bother going to exponential form, or can I just work with the logarithmic form? And the answer to the question is you can do either. You can either work within the confines of the logarithm, so just work with it as is, or what you can do is write in exponential notation. I feel like we should just work with this as is. Okay. And so, oh, sorry, sneezed. X is equal to, now the cubed root of 81, 81 we know is 3 to the power of 4. So this will be log base 3 of the cubed root of 3 to the power of 4. So that means x will be equal to log base 3 of, now the cubed root of 3 to the power of 4. So remember, if you have the nth root of a to the m, that's the same thing as a to the power of m over n. And so consequently, this will be the same thing as 3 to the power of 4 over 3. And this has some artificial difficulty in that a lot of the numbers just repeat as 3. So there you go. And so x will just be equal to, so log base 3 of 3 to the power of something is just that something. So it'll be 4 over 3. Okay, let's continue on. And what do we have? So we have 3 pages left, I believe. So let's have a look. Okay, example 5. So these were the lessons that we studied on the lesson of last time. So for the function f of x is equal to negative times x plus 2 times x plus 3 times x minus 5. It wants us to determine the zeros. So the zeros are going to be, or the x-intercepts if you prefer, will be -2, -3, and 5. We need to sketch this graph. We note that this is a cubic, meaning that it's a degree 3, and it has a leading coefficient that's negative, which means it'll have m behavior from quadrant 2 to quadrant 4. So note, if you want a review of how we saw this, make sure to check out the lesson on lesson 5. There's a chart that'll help tell you the shape of what these things look like. And so when we go ahead and sketch this thing, okay, so we sketch the x-intercepts as best we can. So there's -3, there's -2. We'll put 5 over here. And we start in quadrant 2, and we're going to end in quadrant 4. So that means we must pass through the -3. Ooh, you know what? Let's put this in red. That means we must pass through the -3, come up through the -2, and then pass down through 5 and continue on. Now, if you wanted to be a bit more precise, you could sketch the y-intercept as well, and which could help as well. And so do we want to know if we sketch this correctly? You can just type this into your equation here. So if we type in negative bracket x plus 2 times x plus 3 times x minus 5, you can see we end up getting this curve. And let me stretch out the x-axis a bit, shrink the y-axis. It is. So we end up with this curve. And again, they're roughly similar. But you can see that this graph has a y-intercept of 30 if you were so inclined. But it's roughly the same shape. Okay. Now, I mentioned in lesson 5 that if you didn't want to try to use n behavior and the negative leading coefficient, meaning if you didn't want to or had trouble with or weren't sure of how to apply this information, what you would need to do instead is to use a table of values. And if you notice here, here is that function I graphed over here, and you actually have to sub in quite a bit of these x values to make sure that you have a reasonable graph. So recall that we had x-intercepts at -3, -2, and 5. And so our chart here needed to have x values above, below, in between. So we ended up checking off 5, 6, 7, 8, 9, 10, 11. You had to end up checking 11 x values into this function, where you would type in one at a time. F of -4 is equal to negative times -4 plus 2 times -4 plus 3 times -4 minus 5, and found out that the answer to this was 18. And you can do that. That's perfectly reasonable. It just is quite time consuming to do that. So when a question says graph, this is what you need to do. And if a question says sketch, this is what you need to do. Okay? All right, let's continue on. All right, just making sure. I'm worried about running out of. I'm worried about running out of time, but I think we're going to finish okay. So we're going to expand and simplify the following. So we have 3x multiplied by x minus 3 times x plus 4. So I said the easiest thing to do was to deal with the brackets first and leave the stuff on the outside till last. So this will be 3x multiplied by x times x is x squared, x times 4 is 4x, -3 times x is -3x, -3 times 4 is -12. Okay, simplify the two terms on the inside. Actually, like the green highlighter for this one. Oh, not like that. That was terrible. Let's try again. There we go. Okay, so this is 3x multiplied by x squared. 4 minus 3 of the x variety is just x minus 12. Multiplying out the 3x yields, and remember we want 3x multiplied onto all three terms. We get 3x to the power of 3 plus 3x to the power of 2 minus 36x. Okay. Letter B, we have x minus 1 times x plus 1 times x minus 2 times x plus 2. So recall that this has two sets of difference of squares, where this fulfills the property that if you have a minus b times a plus b, that's equal to a squared minus b squared. And so we're going to work out this two independent steps. I guess I should. No, we'll just, no, too much highlighting. We'll just keep this all the same color. And so for the first bracket here, x times x, x squared, -1 times -1, sorry, -1 times 1 is -1. So there it is. That's what it's going to turn into because it's a difference of squares. For the second bracket, x times x, x squared, -2 times 2 is -4. And that's it. If you were to FOIL this out normally, you would end up getting just a simplification where -2x plus 2x is equal to 0. Okay, next thing we want to do is use normal FOIL techniques. So x squared times x squared times x squared is going to be x to the power 4. X squared times -4 is going to be -4x squared. -1 times x squared is -x squared. -1 times -4 is going to be +4. We're going to now combine our like terms and result in x to the power of 4. -4 minus 1 is -5x squared plus sine of 4 at the end. So all's well. So again, if you have the opportunity to use the difference of squares, make sure to do that. But these questions can get quite lengthy. So don't try to preserve space. Sometimes you just need an extra piece of paper. Okay, question 3. We're going to determine the equation of a given function. F of x is equal to k times 3x minus 1 multiplied by x plus 1 multiplied by x minus 4 multiplied by x minus 2 and that's going to pass through 0, 8. So we're going to make the substitution that x comma f of x is the same thing as 0, 8. So instead of f of x, we're going to write 8 is equal to some k value multiplied by, now it's going to be 3 times 0 minus 1 times 0 plus 1 times 0 minus 4 times 0 minus 2. And note that if you said to me, hey, can I just drop the x values right away? You certainly could have, but I'm just showing the step as if it didn't happen to be an easy 0 for us. So 8 will be equal to k times negative 1 times 1 times negative 4 times negative 2. So these are three negatives multiplied together. So this will be 8 is equal to negative 8k. Consequently, k is equal to negative 1. So we can conclude that our function f of x will be equal to negative multiplied by 3x minus 1 times x plus 1 times x minus 4 times x minus 2. Again, just exactly the same case as a quadratic, just more steps. Determine the equation of the function shown below. So here we can see that this is a cubic. We have x-intercepts of, looks like here, negative 1, comma 4, but that 4 happens to have a bounce on it, so it's going to be multiplicity 2. And so an equation of this will be f of x is equal to k times, so the x-intercepts are x plus 1 multiplied by x minus 4, but it's multiplicity 2, or order 2, it's going to be the power of 2. They gave us a nice point to work with, 2 comma negative 6. So we're going to say 2 comma negative 6 is equal to x comma f of x. So this will be negative 6 is equal to k times 2 plus 1 times 2 minus 4, all squared. So negative 6 is equal to k times 2 plus 1 is 3. 2 minus 4 is negative 2 to the power of 2 is 4. So negative 6 is equal to 12k. So that means k is equal to negative 1/2. So 6 divided by 12 is 1/2 of the negative variety. So therefore, we know that our function f of x will be equal to negative 1/2 times x plus 1 times x minus 4 all squared. Okay, lastly but not leastly, we're going to determine the equation for a quartic function with zeros of negative 1 multiplicity 2, 0, and f of 1 equals 10. So I made a small mistake here. This should be multiplicity 3, otherwise it's not going to be a quartic. And so we're going to have here f of x is equal to k times, now we have just an x value here. So if you have k bracket x, you can write that just as kx times x plus 1 to the power of 3. And it passes through the point 1 comma 10. So we're going to have 10 is equal to k times 1 times 1 plus 1 to the power of 3. And so this will be 10 is equal to 1 plus 1 is 2, 2 to the power of 3 is 8. So this will be equal to 8k. And so that means k will be equal to 5 over 4. And so as our final answer here, we can see that f of x will be equal to 5 over 4 x multiplied by x plus 1 cubed. Now, if you had the situation where it didn't tell you, like if the question goes out of your way to tell the multiplicity, or if it didn't tell you the multiplicity, you might have had to put your own order on this. But I see that we are now out of time, but we also managed to finish up everything. So when we meet on the lesson of next time, we're going to be having a look at solving more polynomial equations, and specifically long division. And that's all we're going to do tomorrow. So with that, goodbye for now.